The next presentation is titled Machine Learning for Construction Process Control, Challenges and Opportunities by Bharath, Sankaran. Are they? Ah,
Yeah.
perfect.
93.
93, yeah.
The next one is 88.
No, 88 was just what happened,
Yes.
the video.
Oh, sorry. I'll do the presentation, share screen, and we can start. That's bad.
All right, perfect. And this is to go forward. All right, perfect. Hey, I'm Bharath, and I'll be talking to you about process control in construction and how you can use ML to address some of these issues. So kind of give you a brief overview of the problem. How do you implement process control, where machine learning AI can have an effect, and what are the practical implications and the challenges that you face when you try to take this on site? So construction, one of the world's largest industries, but also one of the world's most wasteful and inefficient. In fact, not only does it have a huge economic impact, it also has a humongous carbon footprint. But if you think of it, at the end of the day, construction is just on-site manufacturing. So how does it rake up with other forms of manufacturing? Other manufacturing sectors, practically anything that is not construction, has incredibly high economic margins and are close to approaching zero waste. But construction is on the other end of the spectrum. And why is this? It's because they've implemented very efficient process control, and construction lacks process control. So the question is, how do you implement process control in construction? For the control theorist out there, this is a control diagram, but basically process control is you have a reference state, you measure what's going on in the process, compare it to your reference state, and see how the two things have diverged. In construction, you have a wonderful reference state, which is your BIM. It's a 3D model that's evolving in time, so it's 4D. You can compare this to the process on site by capturing the process on site through reality capture. Basically, the BIM is giving you geometry that's evolving. You capture geometry on site, you compare the two things, and you can figure out how they're diverging. And if the geometry is wrong, it's fairly safe to assume that the process is not going well. But there is one practical issue in construction, or if you think about it from a control standpoint, is the system is open and there's a lot of unmodeled noise that enters the system. So what implications does this have? So why is it challenging? First things first, I said the BIM was your reference signal, but the BIM is a living document on an actual construction project. It's not designed once and left as is. It evolves during the course of the project, which makes it very hard. So you have an evolving reference signal. Second thing is the process is extremely nonlinear. The only thing linear is gravitational causality. You can't build floor 3 before floor 2, but everything else in the process just runs whichever way it can. Then it has an extremely dynamic environment, which causes a lot of occlusions. So there's workers, materials, scaffolding, you name it. This causes what you call partial observability. You can't see the site entirely. You can't measure it entirely. And finally, it's a decentralized control problem. So we spoke about a BIM, but actually there are multiple BIMs. Every team has its own reference model and they just go ahead and do whatever they want to do. Outside of the practical implementation issues, you have environmental issues because a construction site is neither indoor nor outdoor. So you get the worst of both worlds. It has both static and dynamic elements, and the dynamic elements have different frequencies of motion. So people walking on site move at a higher frequency versus scaffolding, temporary works, they have a lower frequency. And you have a lot of unmodeled things because a construction site at the end of the day is the storage facility too. So all of the material that comes into a construction site gets stored over there. So you have a lot of unmodeled noise. And outside of the core problem, there are some practical implementation issues. I think Mani might have touched on this earlier, or I'm not sure if he did. The level of implementation of BIM and what actually happens on the construction site are two entirely different beasts. So either the BIM is over-designed for what actually happens on the site, or it's under-designed. A practical example is something like a wall. The wall in the BIM model on any practical construction site is probably designed like a block. What actually happens on the site is this incredible level of detail, which is never captured. So it's very hard to compare reality to design. Second thing is the environment presents a lot of domain-specific low-frequency noise. You have machinery, people, wet concrete, rebar. This is where the stuff needs to work. And here, it's not obvious to find out what is part of the building, what is not part of the building, what is being used to build the building, and what are the different dynamics for each one of these things. And finally, you suffer with the problem of into-the-wild sensor acquisition. So your construction site is plagued by every problem you can think of, and why visual techniques fail very badly when you try to do process control, because you have the lighting of the outside world and the inside world coming together at the same point. And it's a wonderful non-color picture because there's absolutely no texture. In a construction site, everything is gray. So you end up in a situation like this where you're really not sure what you're looking at if you pick up an image that was captured at a construction site. So this actually presents opportunities to apply advanced methods in 3D vision and machine learning to be able to solve this problem. And what I'll be talking about from here on is some directions in how you think about solving these problems. The first direction is trying to think about equivariant models. If you think about it, let's say you have 100 square meter floor slab. The problem on this floor slab could be localized to some corner, but it might be the same problem. There's excess material or there's a void somewhere. And it's the same problem that happens over and over again in different locations within that floor slab. So it's very hard to learn a model for each one of these problems. Instead, what you need to think about is not only build models, machine learning models that are invariant, but they're equivariant. For people who don't have a pure math background, equivariant is basically you take a set, you reorder the set, and you basically have the same thing back. So that's basically equivariant. So when you think about building machine learning models to do construction, cross control or comparison within settings like this, you need to think about equivariance. The second thing is about localizing insights. So if you look over here, if you look at the point cloud associated with this or the image, the only reason you know that this wall is being constructed is because of the cement block right beside the rebar. But that location changes according to which wall you're looking at. So you need your machine learning models to be able to localize their insights, not tell you that something is X or Y, but tell you why it is X or Y. And that actually becomes useful. And the final thing is unsupervised learning. Unsupervised learning is because semantics are very divergent on a construction site. You can get two experts, two project engineers, two architects, show them the same thing and ask them what is going on, and they'll give you two orthogonally different answers. And this has been our experience going on hundreds of construction sites around the world. So what we do is we do unsupervised learning on the data and then use domain-specific knowledge to actually filter out these insights to produce something that's actionable. So what does all of this look like in reality on a construction site when applied? So this is where our solution, these are the kinds of things that we work on a daily basis. This is our bread and butter. If you look at this site, it's very hard to say what is construction site, what is temporary works, and what is material, and where the site is actually evolving. But our algorithms that we've developed can go in and automatically filter out all the low and high frequency noise, which is everything that's just turned red. We extract that noise and try to capture the pure signal that comes out of this. And then we do machine learning on that using some of the insights that I told you about, the 3D machine learning techniques, and then deliver very high quality feedback to our stakeholders, telling them what is built, what is not built, what has been built incorrectly, and if it's built incorrectly, why it's been built incorrectly. With that, I just want to wrap up and thank my wonderful team for all the work that they've done. And just a little plug, we constantly keep talking about how the gender representation is really bad in construction. The way you can fix that is there's an old quote that says charity begins at home. We are almost being close to 50% women in a construction context startup. So if you start where you are, you can actually have a broader impact on the world. With that, I'll take questions. No questions? Awesome.
Are there no questions from the room? If not, I can ask one.
It seems like it.
Yeah.
Yes, Cynthia.
Yeah, no, really great presentation. I'm curious on the practical side, like what have been some of the challenges that you've seen while trying to deploy these like these machine learning models with like real construction projects with real like industry members? What are the things that they are most interested in highlighting? How is this like solving their problems?
Yeah, so practical problems is ultimately we are trying to compare BIM to reality. And the BIM is never a representation of what happens on the construction site. A BIM is mostly an aspirational entity for an architect, and that never gets implemented. So this is one particular problem that we see. Like what I was talking about with the level of detail. Sometimes they have screws and everything modeled, and then the physical construction process is very different. And they're like, okay, these things don't match at all. Or they have something modeled as a big block, but then you have screed, like for instance, a floor slab, then you have screed, and then you have a level of rebar that goes in all, and none of this is modeled. So it's very hard for us to compare. The second thing is, and I think this is mostly because I used to be in academia, I can say it's like because AI ML is so hyped, everybody has an idea of a bad idea of what it can accomplish. These are supposed to be, at the end of the day, models that give you a few insights. They're not magic wands. So you have to use this famous computer science acronym, GIGO, garbage in, garbage out. You can't throw garbage into a model and expect something wonderful to come outside. So if your BIM model doesn't have semantics, you don't capture the data that you're trying to compare. So you're using reality capture, you stick a laser scanner on a construction site, but you don't actually capture the element you want to compare and then ask, why don't I have an analysis on this? It's because the data was not captured. So these are practical implementations, problems that you have on a construction site when you go out there. Yes.
Thank you for the presentation. I have just a short question. Which level of detail do you find useful for the comparison with the construction site?
The level of detail you plan to actually implement on the construction site. So mostly I would say around level of detail 300 works reasonably well. 100 is very, like, it's pretty useless in the sense that everything gets modeled as a block. And then if you're, let's say you have a chamfered column or something, the physical construction process is very different. So we're always going to say that this thing has been built incorrectly. So there's always a divergence. 300 level of detail works fairly well to be able to capture to a reasonable degree what is going on the construction site. And then we let the model absorb the rest of the uncertainty. 400 is a bit excessive because this is the thing, you model screws and light bulbs and this, and you go out with a scanner that can't even capture that. You know, when you walk in with a handheld reality capture device or any of these SLAM-based sensors, they have a noise standard deviation of 3 centimeters. And if you're trying to capture something of like 10 mil with 3 centimeters, no, it's not there. It's physically within the noise range of the sensor, so it's not going to work. So there's use cases, and you have to think about your use case. Any other questions? No? All right, thank you.
Thank you so much.